Well, my name is Brendan Hemley. I'm an independent consultant. I've been involved in transit for a long time. Previous life, I worked at the Canadian Urban Transit Association, and I've been an independent consultant now for 22 years, working both the US and Canada, and very active trying to bridge the gap between the academic research world and the practitioner worlds. So I've been very happy to work with AMR to support the Transit Analytics Lab. It's one of the few places that really tries to reach out and do applied research. So as Amr said, there are 4 sessions today. The first one I will be moderating. It's on transit analytics related to planning and scheduling. And we have 5 presenters, and we're sort of using a slightly modified lightning presentation, but each presentation will be around 10 minutes. And then we'll try to have a little time for questions after each, and start with that. Our first presenter, I'm gonna read them to get the titles exactly right. Alaa Itani is a PhD candidate in the Department of Civil and Mineral Engineering at the University of Toronto, U of T. In her PhD thesis, Alaa is developing guidelines and analytical tools to support on-demand transit planning, ODT planning. So Alaa, take it away.
Thank you, Brendan, for the introduction. Hello, everyone. Good morning. Happy to be presenting today as part of our Research Day. I will talk a bit more about the guiding principles that we've been trying to form the last year based on some synthesis from the research and practice. Today's presentation is going to be a short presentation with some of our research motivation and objective behind constructing these guiding principles and how we did guiding principles for 2 different use cases. The first use case is at the transit network design, and then the second use case at the service planning level. And I will conclude with some of the limitations and future steps. So really to begin with, maybe a lot of you already heard of what's on-demand transit. It's a flexible form of transit that can be served in different types of vehicles, but it also requires some sort of supporting technology to address the traveler's requests of drop-offs and pickups. And I like this definition of Walensky, that it's really the chameleon of the public transportation world because it's not one thing. Actually, on-demand transit comes with different forms. It can change its form in the middle of its cycle, and that's how flexible it is. And here is a schematic from a colleague of ours, Willem, just showing the broad spectrum of on-demand transit, and it could be something more structured towards fixed route transit, or it could be more dynamic, more towards ride-hailing services. And what really differs in these are the service goals. Like different on-demand transit configurations have different service goals, the vehicle size, and the productivity, or we can replace this by the expected performance of these different services. And this wide spectrum is really what makes planning for on-demand transit a challenging task. And from our synthesis of research and practice, we tried to come up with a division of the different configurations of on-demand transit services. The more structured is the on-demand transit first mile, last mile connection, and the most kind of flexible form is the door-to-door configuration. And under each of these, we can also have different flexibility in terms of operation and expected performance. So the motivation of our work was really, as we were synthesizing a lot of the practice, we've noticed that some agencies were doing a major transit network redesign and having on-demand transit projects at the same time, such as Edmonton Transit. And on the other hand, we've been seeing that a lot of agencies were replacing some of their underperforming routes with on-demand transit to have a better efficient operation. So we kind of like noticed that now we have 2 cases here: the transit network design and on-demand transit integrated network guidelines, and some guidelines that are related to the service planning and the continuous service planning guidelines. And that's why we really needed to provide some develop those guidelines for integrated transit planning of on-demand and fixed route transit, focusing on the network design, having fixed route and on-demand transit in one network, and focusing on the service planning and how we can use on-demand transit to end the service planning aspect. So as I mentioned, we focus at the higher level, strategic planning level, the long-term level, and then we go into the tactical planning, which is the short-term planning process. And operations is out of scope of this of these guidelines. So just to begin with, to give you an overview of our first use case, we consider the conventional, if you want to say, transit network design, flowchart, or planning that's usually done. But we try at each of these steps to incorporate on-demand transit, like what are the new set goals and objectives in an integrated network versus a fixed route network or conventional network. What are the adequate performance metrics and criteria? What are the different system requirements, and how can we better help address equity with integrated networks? And again, we also introduce, as I mentioned before, a new set of service configurations into the network, and we talk a bit about the supporting technology that's needed for on-demand transit. And as part of our first use case as well, we try to introduce new opportunities for integration. What we felt mostly common in practice and research is the connection between on-demand transit and fixed route transit, where on-demand transit usually plays the role of first mile, last mile connection. But we try to highlight additional opportunities for integration. The first one, the service integration, which not only entails on-demand transit being the first mile, last mile connection, but also the ability in an integrated network to switch between on-demand and fixed route transit along the same corridor. The second opportunity of integration we highlighted is the FER integration, having free transfers between on-demand and fixed route transit and having the same payment method. Secondly, the trip planning integration, having people plan for their trips, knowing and connecting between fixed route and on-demand transit. And finally, financial integration, because in integrated networks, it's really important to have cross-subsidies between less profitable and more profitable services. And that could be done as well by having joint financial assessments rather than just assessing each individually. Moving to our second use case, which is at the service planning level, here we focus on service-specific guidelines for on-demand transit. And here we start with what are different service goals that on-demand transit achieve at the service level. And here we highlight it could be to increase ridership along a specific corridor by providing adequate first mile, last mile connections. It could be used to understand travel patterns and a new development before implementing fixed route transit and having fixed stops. And as I mentioned before, and we noticed, to replace underperforming bus routes. There's more in the document that we wrote, but this is a glimpse of what different service goals at the continuous service planning look like. We also address the service design parameters, what, how, where, and why to have on-demand transit. We focus a bit on how to develop different scenarios and assess these scenarios with adequate performance evaluation, and finally, how to monitor and go over the service changes and schedule updates with on-demand transit. So this is just a glimpse of a scenario development case where, let's say, a transit agency has potential to implement 3 different types of on-demand transit. The first mile, last mile connection, stops with configuration or door-to-door configuration. There is really a need to have some analytical tools actually to be able to assess, better assess like under which the scenario that best suits the goals of the company. And that would be by measuring from operator perspective, customer perspective, cost, time, but also, like we mentioned, performance evaluation measures that also go beyond cost and time, like vehicle kilometers travels, like mode shift from to transit and the increased in transit ridership. And equity, as I mentioned before, equity is very important with on-demand transit. It has been shown that it can fill gaps in transit networks. So having some equity analysis is important. And finally, the stakeholder consultation before the transit agency can really decide on what's the best plan in this specific service area for our goals and that we need to achieve. So really to conclude here, so those guiding principles really provide transit agencies with a lot of guidance on the opportunities of where to implement on-demand transit, the where, the when, under what conditions, and how. They also help planners really formulate candidate plans of different on-demand transit services and highlight different opportunities for integration between on-demand and fixed-route transit. They provide really guidance on the ways to evaluate those. There's different competing plans. And finally, we discuss also the associated issues of monitoring data requirements and service changes. So the limitation of this work is that I mentioned simulation tools and their importance to evaluate on-demand transit different services, but we do not cover which simulation tool is better or which simulation tool to use. This is part actually of one of our future steps to do some a study on different simulations and their capabilities to model on-demand and fixed-route transit at the same time. The second limitation here is that these guidelines do not focus on integrating on-demand transit with paratransit services or services for with accessibility. And finally, I mentioned equity, and we noticed that there is like kind of a gap in the research with having adequate tools to measure accessibility, including on-demand transit. And this is not part of our research, but it's an interesting research gap. And finally, our future steps, as I mentioned, is really to study the pros and cons of existing tools, collect data, and have some study on travel demand, patterns, demographics, existing transit networks, having a data analysis using some mapping, and finally demonstrate the applicability really of these guiding principles in a real case study at the network level and at the service specific level. Finally, we would like to thank our partners, Region of York, City of Toronto, and NSERC for their fund, and I'm glad to take any questions.
Thank you, Alaa. That was a very concise presentation on a very comprehensive topic. It's a very interesting project. All the ODT experiments to date, almost all of them, have been pilots in specific zones. But this, I think we're now at the place where a few places are taking a more comprehensive effort, like Edmonton or Durham and or Los Angeles. And so it's very timely. Could you just elaborate a little bit more? Oh, wait, there is a question here. Sorry. Aha. Can you, the question is from Daniel about metrics for each use case. I know you touched on that in your guidelines. Maybe you could elaborate a little bit.
Yeah, I think what we highlight in the guidelines is that some metrics might be more important in terms of, so first mile, last mile connection is expected to have a higher productivity, but door-to-door configuration, for example, might achieve a different goal, which may be equity or being in a neighborhood where there's higher seniors. So the emphasis on the performance metric that we look like and those different type of services is different. We're not expecting to look at productivity as the main performance metric when we assess door-to-door configuration, but maybe if our aim is to provide higher connection to transit corridors, then we look at productivity as one of the major performance metrics when we assess on-demand transit as first mile, last mile connection. I'm not sure if I answered your question, Daniel.
Right, it goes beyond performance. I mean, I think reduced wait times or improved transfer times at the hubs, and also it may entail new metrics that are not just efficiency, but more effectiveness and customer
and
convenience.
Improving accessibility, for example, to shopping malls, to nearby areas.
There's another question from Steve. For other right, it has to do with beyond first mile, last mile, other
absolutely
other configurations, and you did touch upon that, or you will be touching upon that in terms of the stop-to-stop, door-to-door, sort of
absolutely,
multiple to multiple origins and destinations.
Yeah, especially with those that Steve mentioned, like shopping centers, medical, the stop-to-stop configuration where these virtual stops are usually landmarks like a hospital or school or shopping mall. This configuration is more suited to address the travel patterns of the specific time. Right.
Okay. Thank you very much. I think we're going to go on to our next speaker. So our next speaker is Margarita Castro. She's an assistant professor in the Department of Industrial Engineering at the Catholic University in Chile. As a postdoc at the University of Toronto in 2021, Margarita worked on the multi-depot vehicle scheduling problem. So we're going to move back into more fixed route specifically. So Margarita, let you know.
Can you start or no? Sorry, can you see my slides?
Yeah, we can see your slides.
Yes, we can.
Sorry. Okay. Thank you so much for the introduction and the opportunity to present here. So in this talk, we're going to talk about how to incorporate service reliability in one of a very important problem to transit agencies, that is the multi-depot vehicle scheduling problem. So first, I want to start explaining a little bit what is the vehicle scheduling problem. So the main idea is that you have a set of trips here that have a starting time, a starting station, departure times that are associated to different routes. And the main idea is to assign these trips in the timetable to buses, so we cover all the trips. So not only is assigning them, but also ordering them. And the main goal is to find an optimal schedule that will minimize the fleet size and also the operational cost. Basically, the distances that the buses has to travel from the end of one trip to the start of the next trip. So the multi-depot version is a little bit different, because here what we have is that we have depots that have a limited capacity. So specifically how many buses we have in each depot. We have the trips as before, and also the operational cost that we can see as travel times too. And we can model this as a network flow model. So as before, the main goal is to assign each trip to exactly one bus. But the difficulty here is that now the bus has to start at the same depot, and this little change makes the problem exponentially harder to solve. And we also have to minimize the costs that basically are the travel times. So here I'm just talking about what we call the deterministic version that has a lot of limitations. Because when we talk about deterministic versions, we're usually talking about solving, considering the times as deterministic. So for instance, we can use average times to solve this problem, which would be optimal for these average times, but they are very inflexible. They don't consider the delays in practice. So we can have a lot of delays, and the scale is not going to be that useful for the transit agency. Another thing that we can do, and this is actually very common in practice, is to optimize overestimation. So you consider not the average time, but you consider that there might be some delays. But the problem here is how much should we overestimate, and what happens in practice is that we tend to overestimate more than we should, and we end with highly cost schedules, but not necessarily with a very good on-time performance, because there's a lot of sensitivity going here. So there have been some studies in the literature to how to incorporate the stochasticity, especially of the traveling times, to this type of problems. So for instance, you can consider the penalty on the expected delays, but this type of work usually don't consider the propagations of delay, that if one trip took longer, probably the next one is also going to take longer because of this propagation. Also, there are some works that try to do some rescheduling or real-time vehicle scheduling, so they try to change the schedule during the operation, but these adjustments might be very infeasible in practice. They require a lot of coordination, so they're not very suitable for practical applications. So in this work, what we wanted to focus on incorporating service reliability, which is a measure that is very important to TRICENT agencies. So here I took a screenshot of the TTC report on June 2021 of this year, and we can see that they have certain targets and metrics. So for instance, for buses, their target is 90% of the services that don't start 1 minute earlier or 5 minutes late. Their target is 90%, but as we can see that day, for instance, it was 70%. And actually, if you check these daily reports, almost never they achieve their goal. So our main focus was to build, with this in mind, was to build cost-efficient vehicle schedules, but also guarantee this on-time performance as defined here for most of the days of the operation. And what we do to achieve this, we develop a stochastic optimization model. So the main key features of our model are the following. Well, instead of trying to optimize over average cost or some overestimations, what we're going to do is optimize over a set of scenarios. So the aim here is to achieve the target OTP level in at least 95% of the scenarios. We don't need it to achieve it all the days, but it should be consistent across most of the cases, where the OTP is basically that 90% of the buses are no more than 5 minutes late every time they have to start a trip. And we model this using what is called probabilistic constraints. Also, these models has a lot of integer variables that make it also very hard to solve, because we have to be assigning trips to depots and to buses. We have to also consider the number of trips that will have delay for each scenario, and the number of scenarios that would meet the target OTP. So to actually solve this model that is very complex, we have this iterative procedure. So basically, we have this first green box here that creates a schedule considering very limited information, just the average times to start. It proposes a schedule, and then we evaluate it over this large number of scenarios. And depending on how it does in those cases, we get some feedback to improve our schedule, and we iterate over this until we can satisfy all our constraints, and we're sure that we satisfy the OTP. So in the end, after this iterative procedure, we return a schedule that has the required OTP in at least 95% of the scenarios. So we first tested this methodology in some toy problems, very small. We have trips that range from 60, 70, or 80 trips, 2, 3, or 4 depots. We randomly generated instances for 5 instances for each of these configurations. We consider 750 scenarios when we were solving these, but we also evaluate the resulting schedule in another 2,000 other scenarios to make sure that it performed well in general. And these are more or less the values. So here in this table, we can see, well, the different configuration, number of trips and depots. We have the mean. That means basically what happens if you solve the problem just with the average results. Then 75% is that you overestimate using the 75 percentile, and then we have our stochastic model. So here we have the objective values. Here is the objective values different with respect to the mean. So if we use average, so our baseline is basically using the average times. And if we use the 75 percentile, we can see that in general it has around 7% more cost on the schedules. But when we were doing our stochastic model that was considering all these scenarios, actually the cost is much less. And the nice thing that we can see also is that If we measure also the OTP, well, with the average results, it wasn't satisfying it. We wanted to have 95%. And here it was around 70, 80. The 75 percentile was it was an overestimation that was too big. So it usually satisfied in all the scenarios, but of course with a higher cost. But the stochastic model was perfect. Like if we can see, it's always around 95%, maybe a little bit more, maybe a little bit less. And the nice thing is that it basically gives us exactly what we wanted at a minimum increase of cost if we compare it to just using average times. So also now we're studying, trying to use the same methodologies to a real case, actually focusing on the city of Halifax, where we have 2 depots, 300 buses, 70 routes, and 4,000 trips. We're in the process of data processing. We're considering the period of winter 2019. We extracted the time direction using the GTFC data, and we're feeding log normal distributions. And we're also we estimated the deadhead travel times between trips using the here data. So we're doing all this data analysis portion to then create the data, to have the data for our stochastic programming methodologies. So overall, to just finish here, well, we propose a novel stochastic variant to this multi-depot vehicle scheduling problem that considers the service reliability. We developed this iterative algorithm to solve the problem with a large set of scenarios. We show that it actually has some value, especially when we have harder problems to solve that I didn't show here, but also we develop a heuristic approach to solve large scale problems. Here I just showed the result for the small ones, but we are almost done with an algorithm that can actually tackle bigger problems. And we're also working in this study case for Halifax, analyzing the traveling times. We're almost done with all the data analysis, and then it's just a matter of creating the scenarios and evaluating the resulting schedules. So this is the end of my presentation. This work was sponsored by Mytex, and one of our patterns was Trapeze. So if you have any questions, I will be happy to answer.
Thank you, Margarita. There actually is a question there from Eric. How do you translate deadhead travel times from here, measuring general traffic, to a bus travel time? Do you include variability in those deadhead times?
Okay, yeah, good question. Yeah, actually, this was very tricky because, of course, the data from here is mostly generic traffic, and it's not bus specific. So what we had to do is, if I don't recall, we added a little bit of variability there, but yeah, basically we use the here data as average time, and then we added a little bit more or less, and I don't recall exactly all the time, but we have to do a little bit of adjustment to make it more realistic. Yeah, that's true. But not too much.
I had a question also. I noticed you tested it with 2, 3, 4 depots. One would assume that the more depots, the more complex the problem, but the results were pretty consistent. Could you just elaborate? I guess it's because of the feedback loop, but you just keep on doing it until. But still, I'm surprised.
Yeah, let me just show it.
This
here.
one, yeah.
Yes. Yeah, so in general, yeah, here what happened is that I'm not actually showing how much time it takes to solve them. It's just the
results.
Objective, the results, the objective value, basically the cost. But in practice, I mean, for this experiment, yes, the more depots that you have, the more variables that you have to incorporate to your model. So it takes much more time. In these particular problems, what we were seeing is that increasing the number of trips was actually makes the problem much more challenging. Like, I think we can reach up to 100 trips, but then it starts taking like several hours to solve. The number of depots, since they're still very small, because in practice you never have more than, I don't know, 5 depots.
Yeah.
It wasn't that much of a problem, but it's true. Like the more depots that you have, the harder it is to solve the problem. But still, these ones were we were able to find optimal solutions in 2 hours, so it was quite reasonable.
Great. Okay. Well, thank you very much. I think we'll go to our third speaker, but thank you very much. Our third speaker is Zahra Ansarilari. She's a PhD candidate in the Department of Civil Mineral Engineering at the University of Toronto. In her PhD thesis, Zahra is developing mixed integer programming models to optimize transfer synchronization in transit networks. Zahra, do you have the screen?
Hello, everyone. You can hear me, right?
Yes, we can hear you.
Perfect. Okay. And you can see my presentation.
Not yet. There we go. There it is.
Okay, perfect. Hello, everyone. My name is Zahra Ansarilari. In this short presentation, I will talk about quickly how we develop a synchronized timetable in a stochastic setting. Okay. So transfer nodes are strategic elements of transit networks, and they provide commuters access to efficient connection across the network. But in many transit systems like the grid network of Toronto, transferring is inevitable, and most of the passengers have to undertake at least one transfer to complete any transit trip. However, without well-synchronized routes, and the utility of transfers might reduce the perceived attractiveness of transit services and also reduce the potential revenue for transit agencies. That being said, not only transit agencies are building timetables for bus routes independently with little or no consideration of timetable coordination, but also transit agencies build timetables without accounting properly for the stochastic nature of transit operations. For example, for the running time, they use average running time or some arbitrary percentile, and then while generating the timetables, which these both practices contribute to very poor transfer experience. And a growing number of studies are tackling transfer synchronization, but mostly in deterministic setting. And the few that they are considering the stochastic nature of transit systems, they're not including enough details in their model formulation. So to address this shortcoming, we are trying to develop as synchronized timetables while we are considering the passenger arrival patterns, which I will explain shortly, plus the uncertainty in running times. So consider a transfer node, and we have one feeder line and one connecting line. The goal here is to develop timetable for a departure time that we are going to publish for passengers. And we have 3 main objectives in our model. The first one is the transfer waiting time, which is the time that passengers from the feeder arrive at their bus stop and then wait until their connecting bus arrives. But as I mentioned, we are considering the stochasticity of the running time. So the arrival time of the buses would not be similar in different possible running time that would occur in real world. So if the bus arrives early, and it has its dwell time, like giving time for boarding and alighting, if it has to wait until the timetable departure, we are adding some unnecessary in-vehicle time to passengers and also extra costs to this bus. Another scenario would be the bus actually arrived very late. So after giving some time for the dwell time, it's going to depart later than the time that it's supposed to, which was the timetable departure time, which is the penalty time, which is, again, we are adding some extra time to the passengers. So the whole idea is to minimize these 3 types of waiting time in our system while considering the stochasticity. So we have 2 main types of boarding passengers. One of them is the transferring passengers, which that based on the arrival of their feeder vehicle and the connecting vehicle, we will have the waiting time for them. However, for the local passengers, it's better to consider the low frequency and high frequency line differently, because in a high frequency lines, the common assumption in the literature is that the passenger will just arrive randomly. So the number of local passengers that we will have in our system. I forgot to mention that we are determining the exact dwell time for our buses to just make sure that we also have the correct departure time. So in order to determine that dwell time, we need to know the number of passengers and also their relative arrival time to the bus. So in high frequency, the local passengers are coming. We define two zones to correctly model this dwell time and the arrival time for the high frequency. So in the zone 1, if it is when the bus arrive actually before its timetable departure time, we will have the local passengers, which is the number of passengers, who arrived during the interval between the previous bus departure time and the arrival time of our bus. And then we will have some transferring passengers. We determine their dwell time and see whether we have any unnecessary in-vehicle time, or actually their required dwell time passes our time departure time, and we consider the penalty. The second case is that the bus actually arrived very late after its timetable departure time. So now the local passengers we have more local passengers. We determine that value correctly, and then we will also have some transferring passengers. Again, we determine the dwell time and the departure time of this vehicle. In this case, for sure, we have some penalty. But the model actually gets more complex when we are talking about the low frequency line, because the common assumption is that the passengers tend to check timetables when their bus is the low frequency and try to minimize their waiting time accordingly. So we will have some skewed distribution for the passenger arrival, and we assume that based on some data, we can actually find the time that the higher proportion of passengers arrive, for example, this time point. And there are also smaller group of passengers who tend to come closely to the timetable departure time. So in order to also consider all of these arrival patterns and the correct dwell time, we define 4 zones for low frequency. The first zone is that our bus arrived very early compared to the timetable departure time, which means that so we will not have any local passengers, but it's possible that we have some transferring passengers. The second zone is that the passenger arrived close at this time interval where we have our first local passengers, so we consider their dwell time plus any possible transferring passengers who arrives during this time. And the third zone is that when the bus arrives very close to the timetable departure time, which is possible that we will experience some penalty time, because if we have a lot of local passengers and also transferring passengers. And the worst case is that the bus arrived later than its timetable departure. So we will definitely have some penalty time so in whole, we are just trying to minimize all these possible waiting times that would happen in our system. In order to formulate this super complex model, we formulate the model through 2-stage stochastic mixed integer programming. The first stage is those timetable departure times, which are going to be fixed. So we are fixing those timetable. We are going to publish that timetable. But the second stage is the possible arrival and departure times that would happen in our system, that we define them as scenario-based. So based on the distribution that we have for our running times, both feeder and the connecting vehicles, we will create some scenarios, and the arrival and departure times of those scenarios are the second stage decision. For example, whether the bus have to wait until its published departure time, whether the bus is departing late or on time. And then the objective is to minimize the expected total transferring waiting time, unnecessary vehicle time, and the delay penalties across all the possible scenarios that would happen in our system. So we are solving our stochastic model through the sample average approximation method, meaning that we are creating those scenarios based on the running time distribution, and then we are trying to solve the model in a way that we develop a timetable that when we apply that timetable in those scenarios, we get the minimum expected value. So we run our model for one transfer node, which has both high and low frequency line. The high frequency is about 3 minutes headway, and the low frequency is 17 minutes. And we run that model for 10 scenarios. And here we are showing the value of solving our model in a stochastic approach instead of using, for example, average values, which is the value of stochasticity. So the green bars are the one that we solve the stochastic model, get some timetable, and then we evaluate that timetable in different scenarios. And this is the total passenger waiting time, for example, in scenario 1, scenario 2, and so on. But if we solve our model deterministically using some average value or some percentile value, which is a common practice approach, and then evaluate that model, evaluate that published timetable through all the scenarios, we will see that some scenarios are performing very poorly and some are performing well. But on the average, our stochastic model reducing the expected waiting times, reducing 10%. And as you can see, the total waiting time that would occur in each scenario is more even compared to when we are using some deterministic model that sometimes it performs well and sometimes it performs very poorly. So as a conclusion, the key finding is that it's worth to have a complex model, solve the stochastic model, because we are seeing more benefit, we are reducing time, and stochastic model can also bridge the planning, can bridge between the planning and operation stage. We will have more efficient operation because we are adding some operational stochasticity in our model at the planning stage, and also using the scenario-based solution method, which we can actually see some disaggregate result and do some analysis for each scenario. As a future extension, one thing is that we can consider the passenger demand uncertainty plus the running time that we already have, and also create an efficient solution method to just solve this model for a larger scale network more efficiently and during a reasonable time. And we would also like to acknowledge the funding supported, the funding that we got from NSERC, City of Toronto, and York region. And I would be happy to take any questions. Thank you.
Thank you, Zahra. That was very interesting. You talked about complexity. The test for your simulation was one transfer point, correct?
Yeah. At this point.
So what happens when in a grid?
Yeah,
where there are a multiplicity, is it scalable or what happens?
Yeah, so there are a couple of approaches that we can like create some solution method to solve a stochastic model that we are currently working on that. That's the point, that you will actually break down the whole model to each transfer node, solve them separately, which is faster, and then merge them together to get the final solution. It's doable, but yeah, it needs some research to do that.
And probably pretty powerful computers.
Yeah.
And then also, could you just clarify the 10 scenarios? I didn't quite understand. Are there variations in the arrival times of the different vehicles? Or the different buses?
The variation here is that the running times between each from terminal to transfer node, now that we have only one transfer node, but we are creating different scenarios based on different running times for both the feeder and the connecting vehicle. And then when we run those models for those different scenarios, the arrival and departure time would be different in each scenario because of the running time. For example, all the buses will depart from terminal at the same time, but because of the different running time, their arrival time at the next node is different. And then we will see whether it can actually depart on time or it will depart later. And then we will see that a stochasticity in arrival and departure time in the following nodes.
Yeah, it's interesting. A lot of transit systems many years ago were structured around pulse to minimize connections, usually at shopping malls or some big hub, which worked in theory and in some places for years, but at some point the random nature of congestion broke it down so that more and more people weren't meeting, and then most of them have abandoned that approach. So this might be a way to sort of get back into it.
The idea still makes sense. Yeah, you just need to make sure that we are considering all the variability while building that model. Then it would work. better.
And the impact on both passengers coming
Yes,
in on the
exactly.
feeder and on board the other bus. Yeah. Very interesting. Okay, I don't see any other questions. So thank you very much, Zahra. That was very interesting. Thank you. Our next speaker, Kareem Othman, is a PhD candidate in the Department of Civil and Mineral Engineering at U of T. In his PhD thesis, Kareem is exploring and developing advanced real-time transit management strategies in urban arterials, leveraging connected vehicle technologies. Kareem, I see you and I see your presentation, although I think you've got the notes showing. Is that presentation mode?
Yeah.
Oh, there we go. Okay, good. Thank you.
So good morning, everyone. So today I'll give you a presentation about some advanced transit management strategies. And let's start with some objectives of what have been done. Like most of transit studies are actually focusing on improving transit speed or improving reliability. So in this research, we actually focus on these two aspects, like improving transit speed and improving reliability. And in addition to that, we are trying to minimize the bus energy consumption, and we are also trying to improve the comfort, the passenger comfort. So it's kind of a combination of objectives. We are trying to achieve improvement in speed, reliability, energy consumption, and the level of comfort. And traditionally, what happens is that if you want really to improve transit or to prioritize transit, this will happen in the cost of traffic. Like you'll implement exclusive bus lanes or TSP, so you are improving transit in the cost of delaying or deteriorating traffic performance. So in this research, we are actually trying to kind of prioritize transit, but at the same time, we are looking at traffic. So we are trying to mitigate the impact of this prioritization on the general traffic. And in this research, we are actually we will be talking about three main strategies, starting with what's called as dynamic bus lanes, speed advisory systems, and some advanced TSP. But for the aim of this presentation, I will focus on dynamic bus lanes and speed advisory systems only. And I will start with investigating every strategy individually. Then I will be kind of combining these different strategies at the end of the presentation. So let's start with the first strategy. So we have dynamic bus lanes, and just dynamic bus lanes are kind of lanes that are accessible to cars when bus is not present. So in this case, we have a bus here, and we have a clear distance ahead of the bus. And in this clear distance, the general traffic is not allowed to enter the lane. But ahead of this clear distance, the general traffic is actually allowed to enter the lane. And behind the bus, the general traffic is actually allowed to enter the lane. So it's kind of giving priority to transit within a specific distance, which is called as the clear distance. And again, this is mainly based on connected vehicles. So we need some sort of communication between the bus and the general traffic to kind of inform the traffic kind of do not really use this lane. So it's mainly based on connected vehicles, and it's very similar to emergency vehicles such as ambulances. And in this case, we'll have a win-win situation. We have a lane that's actually give priority to transit, and in the same time, once we don't really have a bus in the lane, the general traffic will be allowed to use this lane. So we are kind of prioritizing transit, and in the same time, we are allowing the general traffic to use this lane if we don't really have a bus running in this case. So in order to test this dynamic bus lanes, we have actually seen that the TTC in 2019 have approved their 5-year plan, and they actually give priority to 5 main corridors. And in terms of priority, they have implemented the exclusive bus lane in Eglinton East. So now Eglinton East is running with exclusive bus lane. So we decided to run to build the simulation model for Eglinton East and to compare the performance of exclusive bus lanes with dynamic bus lanes, and with the case of doing nothing. Like we will be comparing the case of doing nothing, exclusive bus lanes, and dynamic transit lanes for Eglinton East. And as I mentioned before, like dynamic bus lane is not really going to be affecting only transit. It's going to be affecting transit and traffic. So the main focus here is on the total person travel time, not for transit. It's going to be for total person travel time. And for every we have 3 scenarios: exclusive bus lanes, no priority, and dynamic bus lanes. And for every scenario, we have tested every strategy under different demand levels and different frequency levels. And in this, we have 2 figures here. Figure number A is kind of comparing the performance or the total person travel time for the case of exclusive bus lanes, for the case of no priority at all. And figure number B is dynamic bus lanes versus the case of no priority. And again, in the x-axis, we have the total traffic input flow, and in the y-axis, we have the bus frequency. And again, the colors, the red color is actually meaning that our strategy, which is exclusive bus lanes or dynamic bus lanes, is deteriorating the total person travel time. And the blue one is actually showing that the strategy is improving the total person travel time. So for exclusive bus lanes, when compared to the case of no priority, we'll see that we have an area here under heavy traffic demand and high transit frequency. We have an area here where exclusive bus lanes are actually a good option and improving or reducing the total person travel time. And the same figure is shown for dynamic bus lanes for the case of no priority, but we can see there is a big area here where actually dynamic bus lanes are beneficial. So based on this comparison, we have reached this final figure or this final graph that shows the optimum strategy under every condition. And we can see that no priority at low traffic demand, we don't really need to give any priority to transit. And at high traffic demand with low transit frequency, we don't really need to get any priority. And we have a large area here where dynamic bus lanes will be an optimum strategy that actually that achieve the minimum total person travel time. And the exclusive bus lane is the optimum scenario for high traffic demand and high transit frequency. And now I'll switch to the second strategy. So we have the second strategy, which is the speed advisory system. And the main objective of the speed advisory system is to allow the bus to arrive at the intersection while the signal is green. So what happens is that we have a signal. This signal will be kind of sending the bus the signal timing information. So the bus will be aware of what's happening in the signal ahead, and will be kind of adjusting the bus's speed in a way that allow it to pass the intersection without stopping, to pass the intersection at the green phase. So why are we doing this, or what is the benefits of this speed advisory system? It actually reduces the number of stops, which in turn reduce the energy consumption, improves the level of comfort, and in the same time, it will be achieving the maximum travel speed, as I will show in the next time-space diagram. So this diagram is showing how it works, like how this speed advisory system is working. If we have 2 segments, so what happens is that at the beginning of segment 1, we will be doing the calculation. So at the beginning of section 1, we will be doing the calculation given the signal timing information at signal 1. So we have, this is the maximum speed, this is our minimum speed. So what's happening is that we are iterating from the maximum speed, and we keep iterating until we reach a specific speed that actually allows the bus to arrive at the green phase. But in the case of no priority or no speed advisory, the driver will be traveling at a random speed, arriving at a random time, might stop at the red phase. So here, if you are giving some advisory to the driver, you will be letting him drive at the maximum speed to arrive at the green phase. So for section 2 or for segment 2, we will be doing the same calculations, but the maximum speed is actually hitting the red phase. So we'll be keep iterating until we reach the speed that allows the bus to arrive at the green phase. And this is going to be the speed advised to the bus driver. And again, this way we are actually kind of avoiding the stop at the intersection. So what happens if we have a dwell time? Like in the previous case, I didn't really show any bus stop. So in this slide, I'll be showing how the calculation works once we have a bus stop. So it's going to be not only speed advisory, but it's going to be speed plus dwell time advisory. And in this case, what's happening is that we have the maximum speed and the minimum speed. And for the maximum speed, the bus will be, if we choose the maximum speed, the bus will be dwelling for a specific time, then traveling again. But in this case, if we choose the maximum speed, the bus will be forced to stop at the intersection. And if we choose the minimum speed, the bus will also be forced to stop at the intersection. So any speed between the maximum and the minimum speed will end up in a bus that actually will have to stop at the intersection. So what happens here is that we are kind of even does not really give a speed advisory only, but we give a dwell time advisory. We are advising the driver to dwell for a specific time, for additional dwell time, to allow the driver not to or to arrive at the intersection or at the signal at the green phase. So we have two terms here. We have the standard dwell time. This is the dwell time needed for boarding and alighting, and we are advising the driver to dwell for some additional time to avoid stopping at the intersection. And again, this strategy has been tested on Eglinton East, the same corridor we have tested dynamic bus lanes, and we will be showing the results. Let's start with the average bus speed, and we have the case of exclusive bus lanes and the case of dynamic bus lanes. So we tested this strategy. So in order to make to test this strategy, we need some sort of prioritization to make sure that the advised speed is actually achievable in real life. So we are implementing this strategy in combination with either exclusive bus lanes or dynamic bus lanes. So in this case, we have the two scenarios, exclusive bus lanes and dynamic bus lane, and we have under every condition we have the maximum speed. So the first one is a scenario where the bus driver will be traveling at the maximum speed at every time, and we have S, which is the speed and the dwell time advisory. So for the case of exclusive bus lanes, we will see that the average bus speed is not really different between the two scenarios, and for the case of dynamic bus lanes, it's also there is no major changes in the average bus speed. But in terms of the stop density, which is the number of stops per kilometer, we will see a significant reduction in the number of in the stop density or the number of stops between the case of just traveling at the maximum speed and the case of speed and the dwell time advisory. Around 40% reduction in the two cases, exclusive bus lanes and dynamic bus lanes, more than 40% reduction in the stop density. And in turn, we will see a huge significant or a huge energy savings between 11 to 12% improvement or reduction in the energy consumption. And this is based on the model by Abdul-Adi and Muhammad 2022. So what happens here is that we are achieving a speed that's actually very similar to the maximum traveling speed, but with lower stop density and again with significantly lower energy consumption. And in terms of the level of comfort, we will see this reduction in the number of stops will be translated into a significant reduction in the changes in the speed. So in terms of the comfort, we are translating it into delta V, or the changes in the speed. So for the case of speed advisory, there is around 20% reduction in the delta V. And for the case of dynamic bus lanes with maximum speed, it actually 5% more than the maximum speed with the case of exclusive bus lane. But again, with dynamic bus lanes and speed and dwell time advisory, it's around 15 or negative 16% in the delta V. And for the average traffic speed, the two strategies are achieving the same average traffic speed. But again, we can see exclusive bus lanes are actually kind of affecting the general traffic even much more than dynamic bus lane. So in the future, we are trying to combine these three strategies in a way that actually improve both transit and traffic. So what's happening is that we will be giving transit priority at the dynamic bus lane, and the bus will be communicating with the signal to adjust the signal timing information. We have green extension and red truncation, and based on this adjustment, the signal will be communicating with the bus, giving it the new signal phasing or signal timing information to adjust the bus speed in a way that allows the bus to arrive at the green phase. And for the future, we are actually trying to develop multi-agent reinforcement learning for every strategy of these three strategies individually, and then we'll be combining them for a multi-agent reinforcement learning model. And at the end, I want to thank Hawaii Canada Research Center for supporting this project. And that's the end of my presentation. I'll be happy to answer your question.
Thank you, Kareem. Those are very interesting techniques. There's a couple questions. We don't have much time, but I guess they make a lot of theoretical sense. There's some very practical problems of how you would operationalize it. Question from Willem is about whether you could use, rather than connected vehicle communications, whether you could use lights like on a snow. There are a couple applications of this, I think, in England, where they use overhead signs, sort of like they have on Jarvis or sort of thing. But could you just maybe elaborate a little bit about how practically it would happen?
Yes. So for what I proposed here was mainly based on connected vehicles, but in real life, so there is, for example, we have dynamic bus lanes, and in real life, what's happening is that instead of this connectivity, they use variable message sign to actually communicate the accessibility of the lane to the general traffic. They are, so based on the variable message sign, it will be allowing the general traffic, either they are able to use this lane or not. So it's kind of, and it has been implemented in multiple pilot studies to test like the efficiency of having these dynamic bus lanes, but instead of using connectivity, they'll be using variable message sign, and it was actually beneficial to transit. Maybe in traffic, we don't really have 100% compliance, but at the end of the day, like we have seen like a lot of traffic or drivers are actually kind of following the instructions of the variable message signs. But in the future, we'll have connected vehicles, and it will be kind of easier to kind of enforce this strategy. And for the speed advisory system, it's mainly for transit. It doesn't really need connectivity. It's just it needs some sort of connectivity between the signal and the driver. But you can have some sort of application or a mirror or some sort of a screen for the driver to tell him travel at this specific speed, and it's just advising the bus driver to travel at specific speed. So you don't really need any kind of traffic compliance.
Right, and the holding could be done through the AVL system as well. But there's a practical problem that if the bus pulls over for a minute or so, well, I guess it wouldn't be a minute, but it'd be 30, 50 seconds. Drivers behind in cars would be a little annoyed.
Yeah, that's true.
And in the other case, there's the issue of merging, because with an emergency vehicle, everybody just pulls over and stops, but this would be involving merging back and forth, but it would improve the capacity for both for general traffic as well as improve transit. So it's an interesting approach. I think that sort of covered the questions, but I think we may need to go on to our last speaker. Thank you very much, Kareem. Last speaker for this morning session, Wenxun is a PhD candidate in the Department of Civil and Mineral Engineering at U of T. She will soon defend her PhD dissertation, which is titled Adaptive Transit Signal Priority Algorithms for Optimizing Bus Reliability and Speed Using Deep Reinforcement Learning. Yes, I see your slides. And there, thank you. Okay, all yours.
Good morning, everyone. I'm Wenxun. I'll present my work on a coordinated and bi-objective transit signal priority algorithm optimized using a deep reinforcement learning approach. I'll start with the motivations of our work. Service transit is generally slow and unreliable. Buses do not follow schedule, and sometimes early and sometimes late. We observe missed connections and bus bunching in a lot in Toronto. This is very common in busy transit networks. The transit agencies and users value reliability and speed. Traditional solutions to service problems include network design, route design, real-time route management. However, no strategies can improve headway regularity and speed simultaneously so far. We think of harnessing ITS technologies and advanced AI methods to develop smart route strategies, for example, using transit signal priority, TSP. Conventional TSPs have a few problems. It minimizes signal delay at only individual intersections, typically using simple logic. They are not adaptive to a wide range of situations, especially new ones. They can improve speed, but not necessarily improve reliability. Adaptive TSP algorithms that were developed previously also can improve speed and reliability at individual intersections and is adaptive to new scenarios is not good enough since reliability improvements need coordinated actions at successive intersections. To overcome those limitations, we developed a dual objective TSV that adaptively optimizes reliability and speed, so reliability and travel time concurrently. As transit passengers, we may ask, why not just improve speed only? Why do we want to emphasize reliability or headway regularity? Improving headway regularity and reducing transit delays are both important. On even headways, like long headways, result in crowdedness at bus stops. Short headways lead to bunching. Bus passengers travel on bus lines with irregular headways experience excessive waiting time, which is the out-of-vehicle travel time. In-vehicle travel time is increased when there are transit delays, a great portion of which can be attributed to traffic light. Therefore, we want to develop a strategy that can adaptively improve both headway regularity and travel time, not only at individual intersections, but acting in a coordinated fashion to ensure that the improvement gained at upstream intersections would not be wasted at downstream intersections. We developed a centralized deep reinforcement learning agent to control multiple intersections at the same time. We rely on the infrastructure in Toronto, which are loop detectors to collect transit and traffic data. These data are used for online training of our deep reinforcement learning agent. Check and loop detectors are usually 100 meters upstream of an intersection, whereas the check halt loop detectors are immediately downstream of a stop line, as shown in this figure. The zone between the two loop detectors are called the priority operating zone, POZ. The bi-objective TSP optimization problem is solved using deep reinforcement learning. The algorithm was tested using a case study of two intersections. This slide shows 4 essential elements of reinforcement learning and how they interact. Reinforcement learning is a subfield of machine learning that teaches an agent of how to choose an action from its action space within a particular environment in order to maximize rewards over time. Reinforcement learning has 4 essential elements. The first one is the environment, which is the world, real or virtual, in which the agent performs actions. In our case, is the transportation network, simulated using AIMSA. It includes the 2 intersections used for the case study. The second element is agent, which is the program we train with the aim of doing the job we specify. In our case, the agent is the TSP control system, which interprets the environment state, including information related to bus headways, number of cars, and signal timing. The agent also receives the reward feedback from the environment after an action is taken. The third element is action, which is a move made by the agent, which causes a status change in the environment. We adjusted the duration of green phases at 2 intersections for buses using truncations up to 20, 15, 10, and 5 seconds, do nothing, and green extension up to 5, 10, 15, and 20 seconds. The last element is reward, which evaluates the performance of an action. In our case, the reward consists of evaluations on the headway improvement and travel time at 2 intersections. In general, using reinforcement learning, the traffic signal control system collects information on the states of the environment, takes actions, and learns the quality of different actions via the feedback signals provided by the environment. The proposed coordinated TSV algorithm is trained and tested in a carefully calibrated micro-simulation model using AIMSA Next, which simulated a sub-route network in the city of Toronto. The bus route 36 Finch West, operating on the east-west corridor, experiences high service variability. We collect field data on traffic demand during AM peak and automated vehicle location data from TTC to calibrate traffic and transit performance. All signals along the corridor are simulated based on signal timing cards provided by the City of Toronto. We trained and tested our coordinated TSV at 2 successive intersections to see if the performance of this bus line is improved. The performance of the proposed coordinated TSV is compared with 4 baseline scenarios. The proposed TSV is called DC TSV. That is the dual objective coordinated TSV. So the baseline scenarios are, the first scenario is the no TSV scenario that uses a fixed signal timing plan currently serving the selected intersection without TSV. And the second scenario is Toronto TSV, which uses the TSV algorithm currently implemented in the field, enabled at both intersections. The third baseline scenario is IQL TSV version 1. Well, the IQL TSV are the independent Q learning, uses the independent Q learning approach, which contains 2 different forcible learning agents that were trained independently at individual intersections. The version 1 of IQL had agents trained with all other intersections having no TSV, while the version 2 had intersection 2 trained with intersection 1 having the deep reinforcement learning TSV that were developed previously at single intersection level. All the baseline scenarios are compared with the proposed DC TSV, which contains a centralized deep reinforcement learning agent that optimizes signals at 2 intersections simultaneously. We'll first take a look at the reliability performance. We used coefficient of variation of headway as the measure of reliability, which represent headway adherence. Lower values indicate better reliability performance. This figure shows the coefficient of variation measured at the check-in loop of intersection 1, the check-out loop at intersection 1, and the check-out loop at intersection 2. Ideally, we want to observe that the coefficient of variation keeps decreasing. However, no TSV, the coefficient of no TSV increases, as well as Toronto TSV. This is because these 2 scenarios do not aim at improving reliability at all. IQL TSV version 1 improves headway adherence at intersection 1, but not at intersection 2. This is because the agent trained independently for intersection 2 does not learn how to improve headway with intersection 1 having TSV. The second version of IQL TSV, in which agent at intersection 2 was trained with intersection 1 having a deep reinforcement learning TSV, learned how to improve headway adherence at intersection 2. The proposed DC TSV improved the coefficient of variation from the very beginning when buses check in at intersection 1 until it checks out at intersection 2. It has the best reliability performance. So this slide compares travel time of all scenarios. And each scenario has 3 bars. Blue one on the left is the travel time at intersection 1. The pink bar on the right is the travel time at intersection 2, and the purple in the middle is the segment travel time measured from check-in of intersection 1 to the checkout at intersection 2. So no TSV has the longest segment travel time as expected. Toronto TSV has the shortest travel time because it reduces travel time a lot at intersection 1. And Toronto TSV provides unconditional priority to all buses. However, the travel time at intersection 2 of Toronto TSV is even longer than no TSV scenario. This is because Toronto TSV interrupts the traffic signal synchronization. So TSV fails to prioritize buses at intersection 2. IQL TSV provides travel time somewhat in the middle between Toronto TSV and the longest node TSV scenario. And DC TSV has the second shortest segment travel time. Due to coordination, it has the shortest travel time at intersection 2. Our bi-objective TSV aims at improving headway regularity and travel time at the same time. So we want to ask how much travel time is traded for headway improvement. So we will compare the DC TSV with Toronto TSV, which has the shortest travel time. On average, a 3-second increase in travel time is traded for 7 and 17-second improvement in the standard deviation of headway at intersection 1 and 2, respectively. We performed some calculation and got that these reductions are equivalent to 4 and 7-second savings on expected waiting time for passengers waiting at a bus stop at intersection 1 and 2. As a rule of thumb, the waiting time is valued twice as much as in-vehicle travel time for non-business trips. So in total, this is converted to 22 seconds perceived time cost as in-vehicle time. In conclusion, our coordinated TSV generates the best headway performance. It also brings noticeable reduction in travel time. Comparing it with baseline scenarios indicate that the coordination between intersections improves the effectiveness of TSV. There are some future works. Even though the headway adherence is improved substantially using DC TSV, a centralized control may be computationally inefficient in learning. Therefore, we need to think about developing a corridor-level TSV based on DC TSV. The DC TSV only optimizes bus service in one direction. Future research can consider optimization of service in multiple directions. When the loop detectors used in this study are not able to provide continuous data, this limitation can be overcome by applying connected vehicle technologies, which would support more informative decision-making. Okay, the TSV demonstrated the best performance related to other TSV strategies, but when traffic volumes get high, the performance of this advanced TSV deteriorates, and thus we need supplementary strategies like dynamic transit lanes and speed advisory systems like Kareem just presented. Okay, that is the end of my presentation. Thank you.
Thank you very much, Wenxun. That was very interesting. I liked really how the scenarios and the results from the scenarios were exactly what you would expect given this, how the different strategies are deployed. It's also interesting because I'm not sure many people realize, but the unconditional priority that Toronto has is very unique. The vast majority of more recent transit system TSPs, traffic engineers usually insist on having a conditional priority. So in practice, to put this in place, would this require a centralized TSP as opposed to a lot of them are just intersection based, and they sort of keep a corridor through their predefined plans. This sounds like this would have to be pretty real-time dynamic process. Would it require a centralized control system?
Yeah, I think, this requires a centralized control system. Just like in the very beginning of the formulation page, there's like a centralized control agent that controls multiple intersections at the same time. Yeah, all the state information is provided to the centralized agent for it to optimize the control strategies.
And the learning is a continuous process.
Yes. Usually using deep reinforcement learning would perform offline training first, and then it learned kind of the optimal policy offline. And when implemented in the field, we can turn on the online learning as well. So it learns based on the offline training results and keep learning any new situations that may occur and not captured in the simulation.
That's great. Okay, I think those questions are all related to Kareem's. Okay, well, thank you very much, Wenxun. That was very interesting. We're going to take a break now.